Problem-solving physics electricity for exam success. I was 17 and sitting in a chair, staring at a physics exam paper that might as well have been written in a foreign language. The question showed a simple circuit with two resistors, a battery, and a little box labeled "Calculate the current." I had memorized every formula in the textbook. I could recite Ohm's law in my sleep. But when I looked at that diagram, my mind went completely empty even with the formulas in my head. The answer, when it finally came, felt almost too simple. Nobody had ever taught me how to think. I had been collecting tools without a single lesson on what to do with them. Years later, when I started teaching, I saw the same look on my students' faces. Bright, hardworking kids who knew their definitions but crumbled during tests. They would underline the givens, stare at the circuit, and then start writing things almost at random, hoping something would stick. That's when I began experimenting with a different kind of teaching and started solving problems out loud, every single step, even the ones I normally did silently in my head. I described what I saw when I looked at a diagram, what question I asked first, and why I chose one formula over another. The change in my students was immediate and huge. They began to solve problems they had always skipped before. I made recordings of those sessions, and students asked for more. They listened on the bus, while washing dishes, in the 10 minutes before a test. The audio format did something that a textbook page couldn't. It slowed the thinking down. It let them hear a problem being untangled in real time, and then rewind and hear it again. They weren't just learning about electricity. They were learning how to move through a problem without freezing. This course exists to make the solving audible, repeatable, and impossible to miss. I created this audio course because I believe every student can learn to solve electricity problems with confidence. Not by memorizing more, but by finally hearing how a real solution sounds, one step at a time. Most physics lessons follow the same rhythm: introduce a law, maybe show a quick example, and then assign problems. The hidden assumption is that the space between the formula and the solution is obvious. It isn't. That space is where most students get lost. They know what the individual pieces mean, but they have no reliable way to move from one piece to the next. Exams don't reward you for knowing things in isolation. They reward you for a sequence of choices: what to look at first, what to hold constant, what to calculate next. That sequence is a method, and methods can be taught. More importantly for this course, they can be spoken. A method that you can describe out loud is a method you can actually use under pressure. The path from problem to answer becomes easier when you can hear the steps instead of trying to invent them in silence. The trouble is that most students have never once heard a physics solution narrated from start to finish with all the hidden thinking exposed. Textbooks show clean final answers. This course pulls that silent work into the open. Every worked example in this course is built around a simple but powerful idea: you should be able to listen, follow the thinking, and then imitate it yourself. When you imitate it enough times, the method stops being something you do and becomes something you are. That is why this is an audio course and not another textbook. Listening changes pace of learning. You cannot skim audio the way you skim a page. You have to travel through the thinking at the speed of speech, and that forces a deeper kind of attention. The method you're about to learn is simple enough to remember when you're nervous, and strong enough to carry you through the hardest exam questions. It works because it matches how your brain naturally solves problems. This course is for grade 10, 11 and 12 students who find electricity confusing, or simply too abstract to handle under exam pressure. It's for the student who understands basic ideas in class but blanks when sitting alone with a past paper. The method taught here removes the guesswork from questions and turns good instincts into a repeatable system. If you've ever lost marks because of a unit conversion error or a sign mistake, this course will help you catch those errors before the examiner does. What you're going to gain is a way of working that applies to every circuit problem you'll meet in school. You'll learn what to do in the first 30 seconds after reading a question, how to structure your calculations, and how to check your answer without wasting time. You'll learn to solve problems out loud, because speaking the steps is the most powerful error-catching tool you have. By the end of the course, you should be able to take any standard electricity question, break it down calmly and solve it with a clear chain of reasoning. This course is structured as a journey from confusion to competence. We start by naming the real obstacle, move through the core thinking framework, add a full solving system, and end with habits that make the method stick. Each chapter builds on the one before it, so if you listen in order, you'll feel the pieces click into place. The first stop after this introduction is a chapter about the real enemy in electricity exams. Not a formula, not a concept, but the feeling of not knowing where to start. We'll look at the habits that cause that paralysis and take a diagnostic test to see where you stand right now. That test is not about judgment. It's a baseline, and we'll return to it near the end so you can measure how far you've come. Next comes the heart of the course, a simple decision-making framework for electricity. You'll learn to see every circuit problem as a small story about voltage, current, and resistance, and you'll discover a golden set of questions that sets up every solution. This is the mental skeleton that supports everything else. After that, we'll build a full 5-step solving system on top of that skeleton. This is where the method becomes practical and repeatable. You'll hear worked examples in full audio detail, with every algebraic step and unit conversion spoken aloud. Listen to these multiple times. Each listen will reveal something you missed before. Then we'll tackle the moments when things go wrong. Getting stuck is normal, and so is getting the wrong answer. What matters is what you do next. You'll learn recovery routes, common stuck points, and how to fix them, and a quick reset routine for when exam nerves start to take over. The final chapter is about making the method a permanent habit. You'll get a daily practice plan that takes only 15 minutes, a way to build your own audio summaries, and strategies for adapting the system to any exam format. The goal is not just to pass one test, but to walk into every electricity exam with the identity of a solver, not a memorizer. So plug in your earphones, find a quiet moment, and get ready. The problem that used to stop you is about to become the one you solve first. 1. The real enemy, not knowing where to start. 1.1 The blank page panic. Priya is 15, in grade 10 at a technical school in Durban, and she's sitting in an exam hall with a question that shows 2 resistors in series, then a third one branching off in parallel, and then it asks her to calculate the current through one of them. She knows she has seen this before. She knows she has written notes on it. But right now, looking at the lines and the numbers, her pen doesn't move. Her heart is doing something heavy and fast in her chest. She cannot find the first step. She cannot even see where the first step would be. She has memorized Ohm's law. She has memorized the power formula. She has memorized the rule about resistors adding in series. But none of that is helping her, because there is no starting line drawn anywhere on the page. The freezing is not a lack of intelligence. That is the first thing to understand. It is not that Priya didn't study. It is not that she doesn't care. It is that she was trained, by practice papers, by revision guides, by her own panic, to believe that the answer should somehow come to her whole, all at once, if she just stares long enough. And when it doesn't come, the blank page becomes a mirror. The blank page panic is a learned habit. That means it can be unlearned. But before you can unlearn it, you have to see it clearly. The panic has a shape. It usually starts with a flick of the eyes across the diagram, not really reading it, just taking in the whole mess at once. Then the breath gets shallow. Then the self-talk starts. Where do I even begin? This isn't the one I practiced. This one's different. And then a decision gets made, usually without being spoken aloud. I'll skip this one and come back. But skipping is just freezing with a delay. What you need in that moment is not more knowledge. You need a door. One small, unimpressive door in the blank wall of the problem, and the door just needs to be the first thing you do. It doesn't need to be clever. It doesn't need to be right. It needs to be a step. Here's the truth the panic doesn't want you to know: any step forward, even a tiny one, changes the situation. Write the given values down. Circle the power source. Trace a path with your finger. The moment you do one physical, audible, nameable thing, the page stops being blank. This course is going to give you a specific way to find that door every single time. But for now, in this chapter, we are going to look at the panic, the formula clutter, the classic mistakes, and the silent error machine that runs in your head. And then I'm going to show you a diagnostic test, 3 problems designed to reveal exactly where your starting problem lies. Because you cannot fix a starting problem you haven't looked at honestly. 1. 2 Formula overload. There's a particular brand of confidence that comes from having a formula sheet crammed full of equations. You sit down with 30 formulas highlighted in different colors, and it feels like being armed. Look at them all: Ohm's law, the 2 Kirchhoff rules, the 3 power equations, the energy equation, the internal resistance formula, the equivalent resistance formulas for series and parallel. That's a lot of firepower. The problem is, when the exam paper lands on your desk, you're not being asked to list your but to do something with them. Formula overload works like this. You read a question about a circuit with a battery and a set of resistors, and your brain goes to the formula zone automatically. It pulls up everything. It starts shuffling. B equals IR? Maybe. P equals VI? Could be. P equals I squared R? That's for power loss. The resistors add in series? But there's a parallel part too, so add them inversely? Wait, what is the question actually asking? You don't know, because you've spent the first 4 minutes bargaining with equations instead of reading the problem. And every formula you consider but don't commit to makes the next consideration harder. The mental clutter accumulates. 30 formulas without a decision tree is not a toolkit. It's a junk. You can't see what you need because everything is tangled with everything else. And here's the frustrating part: most students understand each formula individually. They can tell you what V equals IR means. They can solve a practice question that literally says use Ohm's law to find the current. The breakdown happens when the exam doesn't tell you which equation to use. They hand you a story about a circuit and expect you to figure out the tool. That's the skill being tested. More than algebra, more than units, can you choose the right tool under pressure? The way out of formula overload is not to memorize fewer formulas. It's to organize them. And before you can organize them, you have to admit something: every electricity problem is asking a finite set of things. It's asking about voltage or current or resistance or power or energy. That's 5 quantities. 1.3 The classic exam mistakes. Some mistakes are not about understanding. They're about attention. They happen to students who actually know the physics perfectly well. They cost anywhere from 1 mark to half the question. And they are so common, so predictable, that I've seen them appear in examiners' reports year after year, like a signature of the stressed and hurried mind. The first is the unit mistake. You calculate a current and write 2.5 instead of 2.5 A, or you find a resistance and write 10 instead of 10 ohms. It looks small. It is small. But examiners mark for units, and losing that half mark on every question adds up to a grade boundary. The fix is not to be more careful. The fix is to build a habit of writing the unit as you write the number, every single time, not as an afterthought. The second classic mistake is the series parallel confusion. A student looks at a network, sees 2 resistors side by side, calls them parallel, and applies the wrong formula. Or they see 3 resistors in a row, calls them series, and adds them up, even though one of them is actually branched off. This is not a failure of physics knowledge. It's a failure of looking. The diagrams in exams are drawn to be slightly messy, slightly unfamiliar, slightly rotated, and if you don't have a clear mental image of what series and parallel actually mean, the visual noise wins. The solution is not to squint harder. It's to trace the path of current with your finger or your pencil and say out loud, from here, the current has 1 path, so these 2 are in series. But at this junction, it splits into 2 paths, so this branch is parallel to that one. Saying it aloud forces the eye to slow down. The third classic mistake is the sign convention error. This shows up most often in questions with internal resistance or with multiple power sources. A student writes the voltage drop across the internal resistance as a positive contribution instead of a negative one, or they set the terminal voltage equal to the EMF and forget that the internal resistance eats away some of the voltage. The result is an answer that is almost right, off by a small amount, and the student argues with the teacher afterward, but my method was the same. It wasn't the same. It was the same shape without the sign discipline. Sign conventions are easy to state and easy to ignore, because in the rush of calculating, the minus sign looks like a detail. But in electricity, the minus sign is not a detail. It's the difference between energy supplied and energy lost. These 3 units, series/parallel confusion, and sign conventions, repeat themselves across every exam board and every year. They are not deep. They are fixable. But they will not be fixed by saying I'll remember next time, because next time, the same pressure will be there, the same time limit, the same racing heart. The only way to fix a habitual mistake is to replace it with a habitual correct move, and habits are built through repetition with feedback. That's what the audio method gives you, the chance to hear yourself make the correct move, out loud, over and over, until the unit, the tracing, and the sign check become automatic. 1.4. The silent killer, mental calculation. There's a moment in every electricity problem where the actual arithmetic needs to happen. You've identified the formula, you've rearranged it, you've plugged in the numbers, and now you have something like I equals 12 over 6.5. And you do it in your head. You don't write it down. You don't say it out loud. You just kind of feel the answer. 12 divided by 6.5. That's roughly 2, right? So you write 1.9. Then you use that 1.9 in the next step, and the next step, and the next step. By the time you reach the final answer, the error has multiplied itself through every line, And you're off by enough that the examiner can't even follow your method back to where you started. You lose marks not because you didn't know the physics, but because you trusted the silent, hurried machine inside your head. I call mental calculation the silent killer because it never announces itself. It doesn't feel like a mistake while you're doing it. It feels efficient. It feels like what good students do. Good students are quick, right? They do things in their heads. But that's a myth. Good students are not quick. Good students are careful. And careful means externalizing what you can see. When you write down the substitution, when you say the arithmetic out loud, 12 divided by 6.5, so I do 12 over 6.5, that's 1.846, I'll round to 1.85. You create a trail. You create evidence of your own thinking. If the answer is wrong, you can trace back. If the answer is right, you can be sure it's right. There is no such assurance with a number that just appeared in your head. The audio method is built on this principle. Speaking your steps aloud is not a gimmick. It's a break. It slows the mind down to the speed of speech, and at that speed, mistakes become visible. When you say now I multiply both sides by r and then you do it, you are hearing your own instruction and your own execution. If they don't match, you catch it in the moment, not 20 minutes later when you're checking your paper and wondering why your final answer doesn't make sense. The voice in your ear, your own voice, becomes a coach, not just a calculator. Here's a simple test you can do right now to hear the difference. Take a medium difficulty circuit problem and solve it twice. The first time, solve it silently, the way you usually would. Time yourself. Then solve a near identical problem out loud, narrating every step including the arithmetic. Time that too. The out loud version will probably take longer. But check your answers. The out loud version will almost certainly be more accurate, more complete, and more clearly laid out. Now ask yourself, in an exam, which one do you actually want to have done? The silent approach feels faster because it skips the awareness of each step. But the clock doesn't measure feelings. It measures seconds. And the seconds you save by not narrating are given back, with interest, when you're rereading the question for the fourth time because the answer you got doesn't match anything in the options. Speak the steps. Hear the process. That's the core of this course, and it starts with the smallest arithmetic. 1.5. A diagnostic pretest. Before we move into the method, I want you to know exactly where you're starting from. So here is a diagnostic. It has 3 problems. The first is easy, the second is medium, and the third is tricky. Do them now, before you've learned any of the system I'm going to teach you. Don't prepare. Don't revise. Just take 15 minutes, work through them as best you can, and keep your working. Write down what you do, what you think, and where you stop if you stop. This isn't for marks. It's for evidence. Problem 1. A single resistor of 6 ohms is connected to a 12V battery. Calculate the current through the resistor, and state the power dissipated by it. Problem 2. 2 resistors, 4 ohms and 6 ohms, are connected in series across a 20V supply. Calculate the total current from the supply and the voltage across each resistor. Problem 3. A 10 ohms resistor is connected in parallel with a 5 ohms resistor, and this combination is connected in series with an 8 ohms resistor. The whole network is powered by a 24V battery. Calculate the total current drawn from the battery, the current through each branch of the parallel section, and the power dissipated by the 8 ohms resistor. Do them now. Take your time, but don't overthink it. Note where you feel confident, where you hesitate, and where you feel completely lost. The hesitation is data. The lostness is data. Every one of those feelings is a signal about what your brain is missing in its starting routine. Maybe problem 1 goes smoothly. Maybe problem 2 makes you pause at the voltage split. Maybe problem 3 stops you cold. That's all fine. That's the diagnostic working as it should. Here's what I want you to notice when you're done. What was the first thing you did on each problem? Did you circle anything? Did you write down a list? Did you just stare? The answer to that question is the single most important piece of information you'll get from this exercise. Because your first action, or non-action, is where your method lives. If your first action is wait for a formula to float up, then the method hasn't been built yet. If your first action is sketch and label, even roughly, you're already partway there. Write your honest answer in a margin somewhere. We're going to come back to it. This diagnostic is not a one-time thing. It's a before and after. In Chapter 4, after you've learned the full system and practiced with the audio method, you're going to solve these exact same 3 problems again. Same numbers, same circuits. And when you do, you'll have a record of the difference. The difference between now and then is the whole point of this course. For now, just do the problems, keep your working, and note the starting trouble. That's enough. That's the baseline.